All right, so we are going to consider a damped harmonic oscillator shown here, driven by an external force. That external force is going to be written as f of t for right now, and then we'll go and define what that is in a moment. For this system, the equation of motion is going to be mx double dot plus c x dot plus k x equal to our external force f of t. And so rather than having a zero there, we're going to have some type of external force acting on the system. So the general solution of this equation is going to be a combination of a homogeneous solution, which is what we did in the previous lectures when we were looking at free response, and a particular solution. It's going to be a combination of two solutions. Like I said, the homogeneous solution represents the free vibration, and that's going to die out over time, so it's also known as the transient response. And then eventually what we're left with is only the particular solution, which we call the steady state vibration or the steady state solution. Okay, so we're going to let f of t here be equal to capital F times the cosine of omega t. So now we're applying a harmonic force, and then the equation of motion is the same as before, except now we have this harmonic force applying to it. In this case, we are going to focus right now on solving for the steady state response, and then we'll deal with the complete solution on the next page. We're going to do this by providing the ansatz that our steady state solution is x of t is equal to some amplitude big X times the cosine of omega t minus a phase angle phi, where here phi is a constant, as is the amplitude x. Just like with every ansatz, you're going to end up substituting this back into our equation of motion. Then we're going to group like terms, and this will lead to the following. We'll have big X multiplied by the square bracket and the quantity k minus m omega squared times the cosine omega t minus phi minus c times omega times the sine of omega t minus phi. All of that will be equal to, we're going to say here, f times the cosine of omega t what we're going to end up doing is using a bunch of trig identities in order to split the cosine and the sine term into trigonomic functions of only one variable rather than of two variables. And by doing that, we'll end up with two equations that will then allow us to solve for the amplitude x, big X, and the phase phi. And we're going to skip all of the algebra, all of the steps to do that. If you're interested, reach out to me and I'll share with you a paper where they do this. It's like several pages long of calculations. But it does provide a very good insight into how do we go from equation 35 to equation 36 and 37. Okay, so for 36, we're going to get big X times the quantity k minus m omega squared times the cosine of phi plus c omega times the sine of phi. All of that is equal to f. Then we'll get for 37, we're going to get x, big X times quantity k minus m omega squared times the sine of phi minus c omega times the cosine of phi. All of that equal to 0. So you can take equation 37 and you can use it directly to solve for the tangent of phi. You can take everything inside the square brackets, manipulate it, and then find a tangent of phi and determine what that is equal to. You can then use that and substitute it into equation 36, and then you can find a relationship between big X and F, or you can find what big X is. Again, we are going to skip all of that algebra, and I'm just going to give you the solution. So for big X, we're going to get that this is equal to a fraction with F in the numerator, and the denominator we're going to have a big square root, and inside the square root we're going to have k minus m omega squared, this quantity squared, plus c squared omega squared, and this square bracket is raised to the 1/2 power such that it's a giant square root. So that's the amplitude of the oscillation. And then the phase angle phi is equal to the inverse tangent of c omega divided by k minus m omega squared. Okay. So just to recap, this gives us the steady state solution, which is x sub ss. We'll say here t is equal to big X times the cosine of omega t minus phi. The total or complete displacement is going to include both the steady state term and a transient or free response term. All right, so the complete displacement is going to be x of t equal to big X 0 in this case times e to the minus zeta omega n t times the cosine of omega d t minus phi 0. This is our transient term or our free response term because it's got an amplitude that decays or decreases over time. And then plus the steady state, which is going to be x times the cosine of omega t minus phi. And a key thing to note is that in the free response term, we have omega d, and in the steady state response, we have just omega, where omega is the forcing frequency, omega d is the damped natural frequency of the system. So omega d comes from the system itself, and omega is external. It's a frequency that you choose when you're exciting the system, or whatever frequency the system is being excited at, whatever that force comes from. Okay, we're going to write out what this big X0 is. It is not a short expression, and same with phi 0. And x and phi come from equation 38 and 39, so you already have those. Okay, so X0 is going to be equal to another gigantic square root, which I'm going to use the square bracket for. Then we're going to have the quantity x0, that's our initial displacement, minus big X times the cosine of phi, this quantity squared, plus 1 over omega d times the quantity zeta omega n x0 plus v0, where v0 is the initial velocity, x0 is the initial displacement, minus zeta omega n big X cosine phi minus omega big X sine phi, everything in the parentheses squared, everything in the square bracket raised to the 1/2. So you can see here that not only do the initial conditions contribute to that transient response, but also the forcing itself contributes to the transient response. And for phi 0, it's going to be equal to the inverse tangent. I have a big fraction in here. This will be zeta omega n x0 plus v0 minus zeta omega n big X cosine phi minus omega big X sine phi. All of that divided by omega d times the quantity x0 minus big X cosine phi. All right, I'll give you guys a moment to write that down. So when it comes to an exam, you will not be asked to memorize these formulas. Generally on an exam, you'll be asked to just deal with steady state. Usually when we're dealing with a forced vibration problem, we only care about the steady state response and what happens in steady state. We don't care about the transient response because that dies out over time. Whereas the steady state is sustained for as long as that force is applied. There is one homework problem where you will need this, but outside of that, you won't see this on an exam. You will see steady state, and you might see free response, but you won't see them combined on an exam. On an exam, we'd be asking you to analyze the steady state or the free response separately. Any questions? Yeah.
Can I see the steady state for xt? So not the term. Okay.
Sorry, can you see that again? That's what you wanted to see? Yeah, okay, great. Yeah.
I'm kind of confused what phi means in the equation.
Yeah, that is a good question. We come back to way in the past. There is some type of offset in terms of where the system begins. This is for a damped, unforced system, but the concept of what phi is here is going to be the same as in steady state. So there is either a phase lag or a phase lead that the response is following. In this case, we're starting at our initial displacement here, but this is not the peak displacement of the oscillator. It's not the maximum displacement. And it reaches the maximum displacement over here. And so you can use this to describe, this is related to that phi. The phi is the lag, or in this case, it's a lag. How far does the response lag behind where it should be in terms of the peak displacement? And you can see that the period right here to here, this is defined from peak to peak. And we are starting behind the peak due to that phase shift. It's the same thing with the steady state. If I go back down here, same thing with these phis. These are these phase shifts due to the initial conditions and the forcing itself. What I should have shown here, and I didn't plot it here in this response, is that you'll find that the steady state will either be slightly ahead or slightly behind the forcing function or the force itself. So if you plot a comparison of the force, the harmonic force, and the displacement, you'll find that the displacement generally is lagging behind. It generally is slightly behind, meaning that it reaches max amplitude at a later time than the force reaches its max amplitude. And that's this phi that shows up. So what I am showing here is the combination of the transient response and the steady state response shown here. So I've separated them in the top two plots, and then beneath that is the total response with the combination of them, with the red line being the amplitude of the signal, which you can see that it starts off high, decays, and then eventually reaches a constant value, meaning that the system decays to that steady state. This is all done in MATLAB. The code is in the bottom below here. If you want a copy, you can scan the QR code in your notes. All right, any other questions? All right, in that case, we are going to go on. We're going to work on example 3. This is the classwork assignment for today. So what we're going to do is I'm going to read it, and then you guys are going to work on it, and I'll come walk around. And then after, 15 minutes or so, I'll come and solve it. All right, so we're given that a video camera with a mass of 2 kilograms is mounted on top of a bank building for surveillance. The camera is fixed to the building through an aluminum rod, and then there's a wind-induced force acting on the video camera, and it's measured to be the following: 25 times the cosine of 75.3984 T newtons. We were asked to find or to determine the necessary stiffness, assuming zero damping in this case. The necessary stiffness if the steady state displacement cannot exceed 0.005 meters or 5 millimeters. All right, so the key thing that we were told here is that the steady state displacement cannot exceed 5 millimeters, let's say. Steady state displacement, or the amplitude of it at least, is this big X. And if we come back up, we said that our steady state solution is given by equation 34, or big X times cosine of omega t minus phi. The cosine can only be between -1 and 1, so it's going to have, or this x of t is going to have a maximum value whenever cosine is equal to 1, which therefore means that it's going to have a maximum value when it's equal to big X. And so what we're getting from that discussion is the fact that this big X must be less than or equal to 0.005 meters. That's the key to this. The next thing is knowing, and I'm going to come back in a moment, the next thing is knowing what big X is equal to, which we get from equation 38 shown up here, which I'm going to rewrite in a moment. All right, so we know that steady state displacement cannot exceed 0.005 meters. That's just 5 millimeters. We know that the formula for big X is equal to the forcing amplitude, big F, divided by... Oh, wait, I have a different formula here. Hold on. It's going to be equal to K minus M omega squared. This quantity squared plus C squared omega squared. All of that raised to the 1/2. We're not going to worry about the phase phi because we only care about when the displacement reaches its maximum value. We don't care when it reaches that maximum value, just that it does, period. So we don't need to worry about the phase. Next thing is that we have no damping, so we can eliminate that second term. And then we'll get here that this big X is equal to big F divided by M omega squared, because we're taking a square root of a square, so we can just eliminate those two. From here, we then need to go and solve for K. So we get K minus M omega squared is equal to, big X equal to F. K minus M omega squared is equal to big X over big F. We're going to find that K must be equal to big X over F plus M omega squared. Yeah.
Sorry, would it be F over X?
Yeah. Yep, it should be F over X. I got it right. Yeah, okay. From here, we can go and plug in numbers, and this K should actually be greater than or equal to this value, because it's okay if it's greater. This is going to give a lower displacement, so that's fine. We can plug in our numbers here. We're going to get 25 divided by 0.005 plus 2 times 75.3984, this quantity squared. And somebody compute that for me. All right, speak louder. 60,000? 16,000. Okay, all right. Say it again. 16.
16,369.8.
All right, that's good enough. Newtons per meter. And that is the answer to this example. All right, any questions on this? Before we move on into mechanical resonance. Yeah.
What would be the stiffness of this question in terms of offset? Would it be a linear rod?
Can you say that again?
What is the stiffness of this question? Like, it will be like a linear rod stiffness, or?
Yeah, so I mean, I didn't include it here, but you are given the length of this rod, so then you could actually go and do a design. You could go and design the shape of the rod. If that length is flexible, I mean, you can change the length. You could also change that. But otherwise, you'd be looking at, it says a tubular aluminum rod, you'd be looking at what is the diameter of the rod. And that is a question that you could ask and answer with the stiffness. We're not doing that in here, but you could do that. So now that you know what the stiffness is, you can go and use this to design your system. And you could maybe find that aluminum doesn't work and you need to use steel instead. I don't know. All right, any other questions? All right, we're going to move on to a topic called mechanical resonance. We're going to consider a damped harmonic oscillator driven by an external force. Our equation of motion is mx double dot plus c x dot plus kx is equal to f cosine omega t. I'm going to rewrite the steady state amplitude for a moment because we're going to go and manipulate that. Big X is equal to f divided by the quantity k minus m omega squared plus c squared omega squared, all of that raised to the 1/2 power. We're going to multiply this by 1 over m divided by 1 over m. Yep.
Is it k minus m omega squared?
Yeah. Yep. There should be k minus m omega squared. Yeah, I'm going to miss that a lot, so please remind me. Okay, we're going to multiply by 1 over m divided by 1 over m. This is equivalent to multiplying by 1. So we're going to do both sides. Multiply by both sides. On the left, we're going to treat that as 1. On the right-hand side, we're going to separate it and bring it in. We're going to get here, big X is equal to big F divided by m. We're going to bring our m into the square root, which will make it a square. We'll bring it into inside here as well, and we're going to end up with k over m minus omega squared. It's quantity squared plus c over m omega, this quantity squared. All of that is in a square root. We can then rewrite this as a fraction. Here we're going to have the denominator omega n squared minus omega squared, quantity squared, plus 2 zeta omega n, omega quantity squared, all of that to the 1/2, still F over M. So just as a reminder, omega n here is the natural frequency. And zeta is known as the damping ratio. And these quantities we defined in the previous lecture, so you're going to want to go look at the damped free response to find what they are. Finally, we are going to divide by big F, and we're going to get x over f, which we're going to call h here, big H, so will be equal to 1 over m, and the big square root of omega n squared minus omega squared quantity squared plus 2 zeta omega n omega, this quantity squared, all raised to the 1/2. And h is generally known as a frequency response function, or this in this case is the magnitude of that. So we'll just say magnitude of the frequency response function. Or the F or F.
What makes this the magnitude versus like what would it look like if it wasn't?
Yeah, so generally when you go and define these frequency response functions, you convert the force from being real valued into a complex expression. We're going to deal with this in the second half of the class after the first exam. We'll end up doing things like Laplace transforms and then going from a complex domain to a frequency domain and showing us there. Here we're just skipping ahead and ignoring that. It's the magnitude because generally the frequency response function is a complex valued function. This is where the magnitude and the phase come from because it's a complex function. All right. Any other questions? All right. We're going to consider the case when c is equal to 0. And in this case, we're going to get here that x of omega is equal to f over m divided by omega n squared minus omega squared. And then I want you to tell me what happens when omega n is equal to omega. Take a moment and think about it and catch up and then tell me. walk me through that.
Because sigma n squared minus sigma is squared is 0, therefore.
What is sigma?
Sorry, omega.
Okay,
I'm getting very close.
no problem. So you're saying that it doesn't exist because
Well, if f of m over 0 or is it infinite? I guess.
so who thinks it doesn't exist? Oh, we gotta like
I think that as the W or omega approaches the match frequency, the denominator can become very small, and there's magnitude vibrations can become much bigger because of that.
I like that. I really like that way of thinking. So without damping, what will happen then?
It'll just go crazy.
It will go crazy. Okay. What happens in the real world when things go crazy?
Breaks.
They break. Exactly. So without damping, the response goes to infinity, actually. It is not necessarily defined, but it's not zero either. Actually, the amplitude grows with time. You end up with a second term in the solution that is multiplied by time, and it just grows with time. So when omega n approaches omega, this big X is going to approach f over m divided by 0, which is going to approach infinity. And this is what is known as resonance. So if you've ever heard of like a wine glass breaking because you force it at a particular frequency, that's exactly this phenomena. And that is resonance. And it happens everywhere, all the time, in every system. And in the end of chapter 3 of our notes, we will deal with vibration absorbers, dealing with this concept of resonance. But that's like 3 weeks away, so don't worry about it right now. Okay, so if you force at resonance, without damping this, the amplitude will blow up and your system will break, effectively. So now we want to ask, how does damping affect the response? And in this case, we will find here that big X will be equal to F divided by M divided by, if we come back up to our steady state equation, so let's make this laser green. So that term is going to disappear, but the denominator is still going to have a term contributed from the damping, or that zeta term. And so it's not going to be divided by 0 anymore. It's going to now be divided by 2 zeta omega n times omega, or I guess you could write that as omega n squared if you want. And this will be less than infinity, such that the damping will prevent the response from growing without bound, as in the undamped case. That does not mean the response is small. And that does not mean your system will not break because of the damping. It depends on the damping that you've chosen. And we'll see in the next page a plot of what this frequency response function looks like, as well as what the phase looks like. All right, so we're just going to start off with what our phase looked like, and then we're going to write out what it looks like in terms of zeta, omega, and omega n. So starting off with the tangent of phi, this is equal to c omega over k minus m omega squared. We're going to do the same thing where we're going to multiply by 1 over m divided by 1 over m. And we'll get here c over m omega divided by k over m minus omega squared. And then this will be equal to 2 zeta omega n omega divided by omega n squared minus omega squared, such that the phase phi is the inverse tangent of the fraction 2 zeta omega n times omega divided by omega n squared minus omega squared. And that's our phase. All right, so when omega is equal to omega n, we will find here, regardless of whether we have damping or not, we're going to find that phi is equal to the inverse tangent of infinity, again, regardless of what the damping is doing. And fortunately, this is equal to pi over 2. So at resonance, the phase becomes pi over 2, such that the displacement response is exactly out of phase with the force, meaning the displacement reaches a minimum or it hits 0 at the time that the force is reaching its maximum amplitude. And vice versa, the displacement reaches a max amplitude or its max displacement value when the force hits 0. All right, I'm going to scroll down a little bit. So what I've gone here and done is I've plotted on the left the magnitude of the frequency response function, or what we call h here. And on the right, I've plotted the phase for varying damping. And I've also plotted, at least on the left, I've plotted what the damped natural frequency looks like on these plots. So on these plots, direction of increasing zeta is as follows. So that means the damping is going up. And down here, this is increasing zeta. Okay, so looking at the FRF first, the first curve in blue is for 0 damping, and this is where it truly goes to infinite response at the natural frequency. And then we're going all the way down from zeta equals 0.5 all the way up to zeta equals 1, which is a critically damped case. In that case, the damped natural frequency is 0 because critically damped doesn't oscillate, so there's actually no oscillation frequency. As we increase zeta, or the damping, the peak magnitude or the amplitude at this natural frequency decreases. And we can also see how the damped natural frequency is also decreasing following a trend like that. Nevertheless, and I should say that this is plotted on a log scale, so these peaks are very, very high. And so even with damping, you do not want to operate a system at resonance. Now, in terms of the phase, when you go through a resonance, there is a jump from phase going from going from like 0 through pi over 2 to pi without any damping. And with damping, it follows a similar trajectory, just always hitting and going through pi over 2 at the damped natural frequency, but deviating away and eventually converging to pi over time. Okay. MATLAB code provided below. QR code will link you to that code. Any questions on this? Okay, in that case, we're going to go on and we're going to do what is known as base motion. This will be the last thing we cover today. And then on Wednesday, we'll do rotating unbalance and vibration isolation, then start multi-degree of freedom. Okay, so base motion is quite literally where the base of the structure is vibrating or the support of the system is being excited. You can think of cases like an earthquake being a base excitation. Earthquake, it forces the ground on which a building is connected to, and in this case, it's the base of that building that's getting excited. Other examples, you can imagine a ship being excited through some base interaction with the ocean. Other cases, you could have a sensitive piece of equipment in a factory or somewhere, and all of the other machines around it are causing vibrations through the ground that are then causing this base excitation of your sensitive piece of equipment. Okay, so here x of t is displacement of the mass from static equilibrium. Y of t is a prescribed motion of the base, meaning that that's some external influence due to the vibrations of the base, whether that's an earthquake or the total vibrations of the rest of the machines in your building and how they contribute to the ground, or whatever it is. It is something that is prescribed. It's not a degree of freedom. Okay, so our equation of motion for this oscillator is going to be mx double dot plus c times the quantity x minus x dot minus y dot plus k x minus y, in this case equal to 0. No external force acting here, but you could add an external force if you wanted. There's nothing preventing that. We're going to rearrange this equation of motion, and we'll get here mx double dot plus cx dot plus kx is equal to c times y dot of t plus ky of t. And we've split this up like this because I'd said that y of t is prescribed, meaning that you know what it is, or it's not, at least it's not a degree of freedom. And then given that, we can treat this as an external force. Okay, so we're then going to say that y of t is equal to big Y times the sine of omega t. So we now have a harmonic forcing. And given this, we'll get that mx double dot plus cx dot plus kx is equal to k big Y sine omega t plus c omega big Y cosine omega t. We'll rewrite this as big A times the sine of omega t minus alpha, where A, or this big A, is equal to big Y times the square root of k squared plus c omega squared. And then alpha here is the inverse tangent of c omega divided by k minus m omega squared. No, wait, hold on. I'm looking at the wrong line. Alpha here is the inverse tangent of minus c omega over k. Oh. Okay, so by applying a harmonic excitation to the base, this is equivalent to exciting the system with an amplitude A and then a phase shift of alpha. Our steady state response then is going to be x sub ss of t will be equal to big fraction y times the square root of k squared plus the quantity omega c times omega squared divided by the square root of k minus m omega squared quantity squared plus c omega quantity squared, all of that raised to the 1/2, times the sine of omega t minus phi1 minus alpha, where here this phi1 is equal to the tangent or inverse tangent of c omega divided by k minus m omega squared. All right, so then applying trig identities, we can rewrite this as x ss of t is equal to big X times the sine of omega t minus phi, where this big X over big Y is equal to quantity fraction of k squared plus c omega quantity squared divided by k minus m omega squared plus, and that should be quantity squared plus the quantity c omega squared. All of that raised to the 1/2. And this is then equal to omega n squared plus 2 zeta omega n quantity squared divided by the quantity omega n squared minus omega squared. This quantity squared plus 2 zeta omega n omega quantity squared. All of that under a big square root. And then lastly, the phase phi is equal to the inverse tangent of the quantity m times c omega cubed divided by k times the quantity k minus m omega squared. This quantity squared plus this quantity c times omega squared, which is then equal to the inverse tangent of 2 zeta omega cubed divided by omega n cubed plus quantity 4 zeta squared minus 1 times omega n times omega. All right, where this quantity, big X over big Y, is called the displacement transmissibility, and is plotted on the next page. I'll give you a moment to catch up. Okay, so I've plotted here the displacement transmissibility, which tells us how much force is going to be transmitted or how much displacement will be transmitted from the base itself. And we can see that again, we get a very large transmission near the natural frequency of the system. The phase is also equal to pi over 2 at, well, that's not true actually. It's only when there's no damping is the phase, or damping is very weak, is the phase equal to pi over 2 in general. But so this plot allows you to determine, if you know what's going into the base, this will allow you to determine what the displacement amplitude of your system would be, or what the steady state amplitude would be, and the phase based on what's going into the system. Again, MATLAB code is provided, and there's a QR code to scan to get access to that. That is everything for today. So we're going to end early, and if you have questions,